Then, Narukawa Minoji Misa will give a presentation on the efforts of Confidential VM to ensure the privacy of Line Yahoo's AI functions. Hello again, I am Narukawa from the Cloud Infrastructure Unit. I usually work on low-level virtualization tasks. Today, I will explain the mechanism of Confidential VM. I am Minoji from the Cloud Infrastructure Unit. I am usually involved in GPU virtualization and related areas. Today, I will explain the implementation of Confidential VM from an IaaS perspective. I am Misawa from the Server and OS division. I am usually involved in the operation and maintenance of OS for internal servers. Today, from an OS perspective, I will explain our efforts to run applications on Confidential VM. In this presentation, I will first explain the objective, then the concept of Confidential VM. I will explain our implementation on OpenStack in our cloud, and finally, how we trust applications. First, I will explain the purpose of this presentation. Line Yahoo provides services that utilize AI. Some of them involve the input of users' private information. Therefore, on the cloud infrastructure, to process such data, a high level of security is required. Of course, as Line Yahoo, operating in a secure data center is a given, but a security model that doesn't even trust the hypervisor would provide even greater security. Line Yahoo internally provides a private cloud called Flava. As an integrated in-house cloud, we provide various services such as IaaS and PaaS. For IaaS, we use OSS called OpenStack. This time, I will talk about the in-house implementation and provision of Confidential VM to improve the security of AI functions. There were actually examples where Confidential VM itself was being used. On the other hand, Line Yahoo's private cloud uses OpenStack, but OpenStack did not have the necessary features. Also, there wasn't a general method to attest to applications. Next, I will explain what a confidential VM is. Confidential VM utilizes CPU functionality to create an isolated VM environment. Utilizing AMD's SEV SNP feature, you can run isolated confidential VM in the form of a VM. The contents of the VM are also encrypted and isolated from other processes running within the same hypervisor. Intel also provides isolated confidential VM in the form of VMs, using a feature called TDX. This time, we will explain Confidential VM, which provides secure processing based on SEE SNPVM. This diagram shows the overall picture of the system we will be explaining today. I will explain them in order. First, regarding the bottom left part, I will explain how the smartphone application securely communicates with Confidential VM. The goal is to enable the Line app to establish a secure channel with Confidential VM and securely send private information. This is the overall picture, and I will explain each one. This time, there is a premise that the hypervisor is considered untrustworthy. Many might find it counterintuitive that we, Line Yahoo employees, would not trust the hypervisor operating in Line Yahoo's data centers. But to achieve higher security, in order to protect what we want to protect, it is important to clearly define the minimum areas that need to be secure and to minimize those conditions as much as possible. This time, in order to protect Line's very important message information, Line Yahoo's hypervisor, instead of relying on that premise, we envision a configuration where the smartphone application itself ensures its own security. We aim to create a system where even Line and Yahoo employees operating the hypervisor cannot read the information input into the AI. Next, I will explain why smartphone apps can trust Confidential VM. To verify what a confidential VM is, we use something called an attestation report. This is what lies beneath the non-shifting confidential VM. I will now explain what this is. The attestation report records a SHA-384 hash value called measurement. This is the SA384 hash value representing the memory state loaded at the time of VM startup. If these match, then we know that what was loaded at VM bootup is the same. Then, for example, if the measurement of when it started up as expected is recorded and incorporated into the smartphone app in advance, this means that a VM with the same measurement value has booted as expected. On the next page, we will explain this attestation report. So, what specific data does the VM state included in the measurement contain? This would be the initial memory state of the VM. With a regular VM, the BIOS is included, but I don't think there's usually much to be learned just by looking at the BIOS. This time, we will use something called direct kernel boot as the VM boot method. In this case, before the VM starts, not only the BIOS, but also the kernel and kernel options are expanded into memory. It directly boots the kernel. In this method, the attestation report's measurement target configuration includes not only the BIOS, but also the kernel and kernel options. Also, even without actually launching it, if the necessary files such as the BIOS, kernel, and options are available, you can calculate what the measurement should be. Therefore, if this matches the hash calculated by a trusted BIOS, Linux kernel, and kernel options, then the issuer of the attestation report is able to confirm that. We can confirm that the kernel and kernel options are running as expected. The attestation report itself is issued by the AMD processor, and at that time, an electronic signature is affixed by the CPU's key. Using this, we can verify whether the attestation report was issued by a legitimate AMD processor. For verification, we check whether it can be verified with certificates published by AMD. Up to this point, the contents of the attestation report can be trusted, and with the measurements within it, the contents of the VM can be understood, and thus the contents of the confidential VM can also be trusted. Assuming the issuer of the attestation report can be trusted, how can we securely communicate with the issuer of the attestation report? The attestation report has a field where arbitrary data, such as a public key hash, can be embedded. By embedding the public key hash, smartphone applications can use this public key to establish a channel of engagement with the confidential VM, which is the issuer of the attestation report. So far, smartphone apps I have explained up to establishing a secure channel with a trusted party. So, what would happen if the system were tampered with? What would happen if the server were attacked and the VM compromised? I will explain. Using 3 patterns. First, it's when the VM configuration is changed. For example, if the kernel is replaced with one containing malware, or if the kernel options are replaced with something different from the original. This refers to it. In this case, the measurement will change. Therefore, the measurement value recorded in the attestation report on the right side of the diagram will change, and from SmartFanFly's perspective, it will become an unknown hash value. We can detect tampering with the VM. If it is detected that the party with whom the secure channel was to be established has been tampered with, the smartphone application can cancel the transmission of sensitive information. In this way, if the VM is compromised and in its original state, the smartphone app can detect it before transmission and cancel the sending of sensitive information. The second case is when the attestation report was not issued by a legitimate AMD CPU. This includes cases where an attempt is made to forge the attestation report by tampering with the CPU to report different measurements than the actual ones, or when the CPU is not a legitimate AMD processor. In this case, since an electronic signature verifiable with AMD's key cannot be created, the attestation report itself, it will be detected by smartphone apps as a fake that fails verification. In this case, too, we can detect it before transmission and cancel the sending of sensitive information. The third scenario is when an attacker attempts to impersonate a server using an attestation report legitimately received from a confidential VM. In this case, the attestation report itself will pass validation as a legitimate report, and the measurement will also be correctly listed. However, in this case, the smartphone app will attempt to establish a secure channel using the public key of the real VM that issued this attestation report. The corresponding private key exists only within the confidential VM. Therefore, since there is no choice but to use a different key, the public keys will not match, and thus a channel will not be established with the attacker's server. In this way, the smartphone app can detect that the recipient is not the expected confidential VM before sending, and thus cancel the transmission of sensitive information. In this confidential VM configuration, when a smartphone app connects to the confidential VM, the VM is running on a legitimate AMD CPU, and we can confirm that the kernel is operating as expected without any tampering, even considering the possibility of destruction. On top of that, we can establish a secure channel and send information externally securely. Next, I will explain how to implement confidential VM using Flarman's OpenStack. In implementing confidential VM in Flava, we carried out the following 2 points. The first is to enable the launching of confidential VM. Since OpenStack did not support SEV NP, we implemented it to enable confidential VM to start. The second point is that we enabled pre-configuration of the BIOS, kernel, and kernel option using a mechanism called direct kernel boot so that an attestation report can be obtained and verified. Furthermore, we passed the certificate to the VM so that the attestation report could be verified. So far, we have discussed the overall picture, and from this point on, we will explain the right-hand box that includes the hypervisor. First, I'll talk about the first point we implemented, enabling confidential VM startup. We have implemented SNP compatibility in OpenStack by passing settings to virtualization middleware called libvirt. By implementing it in this way, users will be able to launch confidential VM in the same manner as regular VMs. Please see the confidential VM startup method example in the next frame. As for changes, we will adapt the OS image for confidential VM and change what is called the flavor, which represents the number of CPU cores and memory capacity, to confidential VM. And then, we pass the user's application container image as an additional parameter. In this way, the confidential VM can be started. In the next slide, in addition to the SEV's SNP implementation, I'd like to introduce the necessary changes and our upstream contributions. Since the hash value of the container image and other information were required as kernel parameters for the official confidential VM, the character limit for kernel parameters handled by OpenStack was exceeded. Therefore, we extended the options passed to the kernel to allow strings longer than 255 characters. The content I have described so far in the slides is currently in OpenStack AppStream. We are moving forward with proposals and bug reports. We plan to release our development documents and source code, and in the future, we hope to make this functionality available to external OpenStack users as well. Above, I have described the implementation up to the launch of confidential VM. From this point on, I will explain the mechanisms necessary to make the attestation report verifiable. First, to verify the attestation report. As I mentioned earlier, it is necessary to use direct kernel boot. Please take a look. When creating a VM, we create it using an OS image. So with a regular VM, we only use the OS snapshot as the OS image. However, with confidential VM, in addition to the OS snapshot, the VM BIOS, kernel, and kernel option are explicitly handled as a set in the OS image. In addition, we allow users to launch application containers and a specific container image separate from the OS image. This separates the OS image creation timing from the user application creation timing. We guarantee that neither image has been tampered with by a third party. In the next slide, I will now discuss certificates. Excuse me, when NPM validates the attestation report, we use VC certificates. These are necessary when verifying that an attestation report is genuine. Also, a unique VCX certificate is issued for each CPU chip and can be obtained from AMD servers. We made sure to store the VCIC on the physical server in advance. There are two reasons for this. One is that VMs are operating in an environment isolated from the internet and cannot access the AMD server. The second is to enable the acquisition and verification of the attestation report even when the AMD server is not operating. Thus far, we have explained the mechanism for verifying the attestation report from the VM user, as well as how to implement confidential VM using OpenStack and Flava. From this point forward, I will discuss how to deploy applications that provide services. Service applications deployed on confidential VM. This makes the application on the user's side trustworthy. This means that the user's application can decide whether to communicate with that service and promote sensitive information. The deployment of service applications that I am about to explain is a part of the overall system. This is the area within the confidential VM, as shown in this bubble. The fact that the kernel parameters are included in the attestation report measurement, which was explained in the first half of this presentation, becomes important for verifying whether it is a trusted service application. For more secure communication between mobile applications and service applications, which is our objective, the service running within the confidential VM, it must be in a trustworthy state for the user. What exactly is a trustworthy state? Then I will explain how we achieve that. So what exactly is a trustworthy state for a service running within a confidential VM? In this initiative, we define a trustworthy service state by the following two conditions. First, the service starts without the specified content being altered. The second is that services are not altered after startup. As shown in the center of the diagram, the service here consists of the OS and application containers. In other words, the goal is for the OS and application container to launch exactly as specified and remain unchanged after launch. If these two conditions are met, users can make trust judgments based on the service actually running. So how do we achieve this state? In this initiative, we have achieved a trustworthy service state through two mechanisms. The first is the specification of services through kernel parameters, as shown on the left side of the left diagram, and this is a mechanism to link it to the attestation report. We specify the OS and application containers using kernel parameters and reflect that information in the attestation report's measurements. This allows the client to verify which OS and application containers have been launched. The second is the OS configuration to prevent external tampering after service startup, as shown on the right side of the diagram. This allows the service to remain in an unaltered state after startup. Next, I will explain how to specify and launch services using kernel parameters, and then I will discuss OS settings to prevent post-launch modifications. As shown on the left side of the figure, we embed hash values representing OS and application containers into the kernel parameters when confidential VM is launched. If the content of the OS or application containers changes even slightly, their hash values will also change. Each hash value is referenced by tools such as dmverity and our in-house container launcher, as shown in the center of the diagram. Additionally, our in-house container launcher refers to the digest of the container image. It retrieves and launches a container with the content specified by that launch value. On the next slide, we will explain which tool handles each hash and how. DMVerity is a tool that can detect changes in the contents of the root file system. The OS updates so far actually refer to the root file system. As shown on the left side of the diagram, the root file system contains all the software necessary for running the service. For example, libraries and configuration files. DMVerity provides a root hash as a representative value for the entire root file system. As shown from the left to the center of the diagram, if even a part of the root file system's content changes, the content of the root hash also changes. If the content read from the root file system changes while the Linux kernel is booting, subsequent processing can be stopped. With DMVerity, the root hash value is specified in the kernel parameter. Therefore, as shown from the center to the right of the figure, the contents of the root file system will be included in the attestation report's measurements. This means that clients can verify which root file system the service is running on. By utilizing these functions and presenting the root file system to the Linux kernel as read-only, this ensures that the root file system, which the client expects, boots without being tampered with. On the other hand, if the root file system is presented as read-only, changes required for service startup will also become impossible. What to do about that will be explained on the next slide. In the operation of this confidential VM service, it's not that no files are written after the confidential VM starts. For example, there are rights necessary for providing services, such as acquiring container images or generating temporary files. Therefore, we use OverlayFS to layer a writable memory-based layer on top of a read-only root file system. Although it appears as a normal writable file system from the service, actual changes are stored in an overlay layer in memory. The root file system itself, protected by DMVerity, will not be modified. Therefore, if there are no changes, the content will be read as is, as shown on the left of the figure. If there are changes, they are saved in memory as shown on the right, and the content is read after the changes have been made. This mechanism allows the service execution platform to remain unchanged while still accommodating necessary service modifications. Additionally, the hash of the root file system targeted by attestation also does not change. Up to this point, I have explained the details of the OS for services running on confidential VM. Next, I will explain application containers. The contents of application containers can be verified using the digest hash of the container image. As shown from the left to the center of the diagram, if any part of the container image content changes, the hash of the container image also changes. As shown in the center to the right of the diagram, by including this container image hash in the kernel parameters, changes in the container image will be reflected in the attestation report measurement. Therefore, clients can verify the contents of the container that started before sending data. Next, we need to actually launch the service application container using this hash. I will explain the boot mechanism next. Application container startup is. This is performed by the service application launcher located at the bottom center of the diagram. First, the launcher obtains the container image digest included in the kernel parameters. Next, it retrieves the container image specified by that digest from the container image registry and launches it. Here, the service application launcher is contained within a root file system protected by DMVerity. Therefore, the launcher itself also starts without being modified. As a result, using a container image digest. The specified application container is also launched exactly as specified. Up to this point, I have explained that we can achieve a state where the OS and application containers can be launched without modification to the specified service content. Furthermore, the attestation report now allows us to verify which OS and application containers have been launched. To make the service trustworthy, we must also ensure that the service cannot be altered after boot, which is the other condition. What the attestation report guarantees is the state of the confidential VM at startup. If one were to log into the OS after booting, by changing settings or replacing binaries, the state confirmed in the attestation report can be altered. Therefore, we prohibit access after a confidential VM is launched. Specifically, SSH login and console login are disabled. Therefore, it is not possible to log into the OS and perform operations after confidential VM starts up. As a result, we have achieved a state where users, such as clients, can trust the service. On the other hand, even if users cannot SSH, as I've explained, they can launch applications simply by specifying the container in the kernel option. First, we explained that by utilizing the attestation report provided by SEEE SNP, a secure communication channel based on attestation can be established between a confidential VM and a remote client. Next, we introduced the implementation for using SEVC SNP confidential VM on OpenStack. We are developing features to create and manage SEEV SNP VMs from OpenStack, and we are also working on contributing those results upstream. Finally, I introduced a mechanism to extend the scope of trust, not only to the confidential VM itself, but also to the application containers running within it. This concludes our presentation. Thank you very much.